related rate problem. Rate change in respect to time. So related rate problems, we're looking at when one quantity increases, what was it due to the other quantity that we're measuring? So quantity X changes in respect to time, then any general quantity Y that depends on X also changes with time. So what it's saying is, if we are differentiating in respect to f of x naught, see how it's not over? Like normally when we do a derivative, it would be d of y over x. Well, now this one is saying if I differentiate y in respect to time, that's the same thing as taking the derivative of the function and multiplying it by the derivative of the time function. It will make more sense when we go through this sort of stuff. So like, for example, when a balloon expands, the radius increases. So because volume and surface area are related to the radius, they will also increase at a uniform rate. They're going to be different, but the radius, when the radius changes, it always will affect the volume and the surface area. Does that make sense? We have change the radius, it's going to change the amount of any formula with radius in it. Okay, so for a spherical balloon, if the radius changes as a function of time, the surface area will also change as a function of time. The rate of change in the surface area with respect to time can also be determined by differentiating both sides of the surface area equation with respect to time. Got it? You have everything. All right, so let's do some math. I feel better when we do math. Okay, so what do we know? We know the surface area of the sphere is equal to 4 pi r squared. That's the formula I gave it to you in that little blurb there. All right. So we are going to do the derivative of this side and the derivative of this side. Okay. We're differentiating both sides of the equation in respect to time, not to the other variable. So it's not going to be the differential of A over the differential of R. It's going to be, I'm not going to use SA, I'm just going to use A for right now, just because it makes a little bit more sense. In relation to time, because we're looking at rate problems, right? We're looking at possible rate problems. So we're differentiating this side in relation to time, and we're also going to differentiate this side in relation to time. There is nothing that I'm going to do to this over here. This is just going to sit like that. It's the derivative of the area in relation to time versus the derivative in relation to time. So let's go back in time. Back in time to your second lesson of derivatives. D2. Derivative with a coefficient on a variable. You guys remember what to do? I read right now, we forgot that because we've never used this one. So this is going to stay the same over here. This comes out front and gets multiplied by the derivative of this. Now that's from D2. That, moving that 4 pi out is D2. Why wasn't it 0? Because it's not a constant by itself. Like a constant by itself, like if you were going to take x plus 2 and do the derivative, 2 is gone, right? And we're left with 1 as an answer. This is a coefficient on the single variable. That was way back when we did crazy stuff like that. So what is, now you're going to use your rules. What's the derivative of r squared? I'm so proud of you. It's like, it's just super fun. And that's multiplied by the derivative of radius in relation to t. So we would have the surface area expands at a rate of 8 pi r times by the derivative of r in relation to t. So what we've done here is we're creating a derivative in relation to time instead of radius. That makes sense to everybody? Before we used the two variables that were in here, now we're adding time because we're dealing with rate problems. So this is a derivative. Okay, so slightly confusing. So had we done this, like had you have done this in relation to r, if you had taken dA in relation to dr, that's super easy. You would take the derivative of 4 pi r squared in relation to radius, and that's just your standard issue derivative. So that would be dA over dr equals 8 pi r, right? This is what we've done all the way along, right? You guys can do this in your sleep. You've done it, you showed it to me, you can do this in your sleep. Now I'm making you do it in relation to time. Radius is increasing at a rate, so it has to involve time. So now I've added a third dimension. How do you feel about that? Great, perfect. Super excited. All right, here we go. Life's going to be delightful from here on in. Okay, let's move on. Okay, given two variables that are functions with respect to time, so x of t and y of t, we've been given a function, and we know that the derivative of y in relation to time is equal to 3. It wants us to calculate the derivative of x in respect to time when y is equal to 2. Easy, right? So we know that dy over dt equals 3. We're currently trying to find that. That's what we're trying to do. That's our big goal. So if we were to, we're going to take one side of the equation. So the whole thing is we're going to differentiate both sides of the equation. So we're going to take x to the exponent 4 minus y to the exponent 4. And we're going to differentiate that in respect to time. And we're going to differentiate 65 in respect to time. You guys good with that? So we're differentiating both sides, not in respect to x and y, but respect of the both sides of the equation in respect to time. Right? Let's go. Easy peasy. So we're going to break this up. We're going to differentiate x to the exponent 4 in respect to time minus the differential of y to the exponent 4 with respect to time, and we're going to differentiate the constant in respect to time. Okay, so let's differentiate. Differentiate x to the exponent 4. You guys can do that in your sleep. Or x cubed. But because it's involved with time, we have to multiply that by dx over dt. Okay. So this is going to be 3y squared times by what? Y prime. What's another way of writing y prime? Yep, dy over dt. I'll put this in for right now. And then what is the differential of 65? 0. Yep. Well, whatever. You want to get, where did I get that from? I don't know. I'm just going to put 0 there. Because that would be times by d of a constant, which is 65 over dt. That's all equal to 0. So this I'm going to rewrite. So another way of writing that, just so we're consistent. Oh, I still got it wrong. Jeez Louise. How does that make you guys feel? Oh, awesome. Okay, so what did the question tell us? What piece of information did the question tell us? Right. So would you have known that y prime is the same thing as saying dy over dt? Possibly. And if you knew that, you could have left it like this, which I would have been fine with. But I wanted to write it like this just so you can see how it's attached to the information given in the equation. So what I know is 4x cubed times by d of x over d of t minus 4y cubed, which I finally got right. What's the value of this? You guys, it's in the equation, or it's in the question. 3, and that's equal to 0. So I've got 4x cubed times by dx over dt, which this is what I'm trying to find, minus, oops, that's supposed to be a subtraction, minus 12y cubed equals 0. Well, that's exciting. No, nobody's excited about that. All right, so where do I need, here's my problem. I have 3 variables. I have x, I have y, and I have the differential of dx over dt, which is the thing I'm trying to find. You know this. You know the variable y, because that's also given in the question. What was it? 2. Okay, so we know that. If we know that y is 2, could we solve for our x? Yes. So because I have 2 definite unknowns, I know what this is, but I have 2 definite unknowns, I need to solve for one of those. So how am I going to solve for it? I know that y is equal to 2. That's a key point. That was going to be in the question. Where am I going to put that in order to solve for x? The original. So it was x to the exponent 4 minus 2 to the exponent 4 equals 65. That one was x to the exponent 4 minus 32. To the exponent 4 is 32. Thanks, guys. Is it only 16? See, this is why I need you. I can't differentiate and I can't multiply. I'm not turning out to be a very good computer. So that's gonna be 81. I think I did that, right? What do I do with that, Jonah? Any suggestions? Okay, so I'm gonna do the fourth root of both sides. What is the fourth root of 81? Ah, you used a positive principal root. What are you missing? Right? Because we know we have a quartic function. The fourth, actually, it's going to be circles. It's going to cross twice. So we're going to have two answers here. So now with this information, you're going to do this twice. You're going to do this when x is equal to positive 3. So we go back to that original equation where we had 4y cubed times by dx over dt minus 12. Oh, sorry. Please. You know what? Maybe we just should have canceled class. You're so kind to me. 12. No, you really don't want to stretch yourself out too much, right? No. 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 Because then you're going to say, but I had a physics test, and I can't do it. So can we push it off to next Saturday? And then nobody's going to show up. Oh, what? Okay, what was that that I was supposed to put in there, but didn't? Thanks. Somebody really needs to supervise me today. What is y then when it's over there? 2. 3 to the exponent 3 is 27. 108. So I got 108 times dx over dt minus 96 equals 0. So bring 96 to the other side. So I'm going to have dx over dt is equal to 96 divided by 108. So dx over dt is equal to. All right, so now what am I going to do? I'm going to do the other one. What's going to change? Is this math, I promise I'll be better at. So I'm going to do -3. So I'm going to have 4 times -3 cubed dx over dt minus, is the 96 going to change at all? No. Because that's getting a 2 substituted in there, right? Oh, that should be a 12. So I'm going to have a -108 times dx over dt minus 96 equals 0. So dt over dx over dt is equal to a negative 0.89. Those would be your two answers. Woo, you only have like 10 more minutes to go. Okay, I feel like that was a big warm-up. Feel like I promise I'll do better on the next one. Okay. So a lot of people say, well, if a side is increasing, if it's doubled, then the volume will be doubled. And that's a misnomer because things are increasing at a different rate. So this is doing the size of the square increasing at a rate of 4 centimeters per second. How fast is the area increasing at the instant when each side of the square is 20 centimeters? Golden. You're going to be great. So let's talk about setting up some variables. So we have a square. What do you think about squares? What do we know about their side lengths? They're the same. What do you want to call them? Sure. So x is the side length. What else is involved in this question? Yeah, the rate. That gives us the rate. What are we talking about increasing? The side length and the area. So we'll say A is equal to area of square. That's exciting. We're finding our variables. And the last thing is, what is our rate measured in? Centimeters. And then what's this one? Seconds. So T represents time in seconds. So what do we know this rate is? So let's talk about, so we have our three variables. We're going to be differentiating x in respect to A or respect to T. T. Everything's time. And this is a rate problem that tells us its length over time. So we're going to differentiate x over T, and we actually know what that is. That's 4. Right? So what will be the other thing that we're trying to find the rate of? The area. So that one's going to be the d of A over d of T. That makes sense, everybody? So we're looking at the rate of the sides versus the rate of the area is increasing. Okay, now we have the equation. I want you to dig deep for this one. I want you to write an equation that relates area to the side length of the square. So you need an equation, and you all know it already. What's proud of you? Proud of you. Had to dig deep for that one. Right? So once you have the equation, we're going to differentiate both sides. So d of A over d of T. Oh wait, that's what I'm looking for. And now I'm going to differentiate my x squared over d of T. All right, so there's nothing actually to do on the left-hand side here, but there's stuff we can do on the right-hand side. So d of A over d of T is equal to, can you differentiate x squared for me? Brilliant. 2x times by the rate, right? And you're already in the fancy group saying it's 4. But there's also another piece of information in the question. So I have a variable here, a variable here, and a variable here that I actually know. So I still have 2 unknowns, but I actually don't because I know what that is. It tells me in the question. What's that one? 20. So dA over dt is equal to 2 times 20, because that's when we want to know when it's going to happen, times 4, which is my rate. So if I'm multiplying all that together, 160. 160 what? There's a lot of mumbling there, but is it meters or centimeters? Centimeters squared per second. Because we're dealing with an area, so it's going to be centimeters squared. So if the side length is increasing by 4, your area is going to be increasing by 160 when the side length reaches 20. Are you guys good with that? That one was way easier. You know what? Maybe that should have been the first question. Yeah, let's scare it. Okay. Well, using a vertical science to experiments in physics, students set up a circular wave that travels over the rate of 12 centimeters define our variables. Let's define our what's our variables in this? T for time. Perfect. What else? What do circles have? A radius. So our, too bad I can spell radius, we can do better there. Okay, so we got our denominator. What's the other thing that we're looking for? Area. Okay, that's exciting. Look at us, we're much better at this. All right. So what do we know? What information do we know for sure? What's the radius increasing at? So it's the dr over dt, which is increasing at 12 centimeters per second. So we have that one. What are we trying to figure out? Right, so in part A, we're looking for the rate of the area, and part C, we're looking for the area. Oh, and part D as well. So we're looking for dA over dt, but we've got a couple different situations, A, B, and C. So it will be different in all of those. But what won't be different is our equation. So step one, we're defining our variables. Step two, you're going to create an equation. And you're going to create an equation that's relating A to R. You're not going to have to reach R for it. So what is the relationship when we're dealing with circles between area and radius? That's circumference. So area is equal to pi r squared. You guys all know that, right? Like that's a given. You know that for sure. So we're going to differentiate both sides. It looks pretty scary, but then it's not really. What's this going to be? By differentiate. Did I differentiate that correctly? Okay, so this is the equation in respect to time. What do we know? What piece of information do we know over this? We know this one, but it's that 12, right? So you've created the equation. I'm just leaving that here for right now because there's different pieces of information for A, B, and C. So let's do A. What did A tell us? It wants to know the rate that the area is increasing when the radius is 6. So we know that R is equal to 6. We also know that dr over dt is equal to 12 centimeters per second. So all this is substituting information, which doesn't seem too hard unless you're me and can't figure out how to multiply. Let's leave it in respect to pi. Is everybody okie dokie with that? Let's not get irrational. Twelve times 12, 144. Call gross. Somebody wants to do order gross or something, they want 144 items. There you go. There's a fun fact for today. Why is the baker's dozen 13? I wonder if that's it. You bake 13? Because the baker's dozen is 13. But a regular dozen is 12. So maybe it's a house take that for with somebody. I'm not sure. Bakers are sketchy there. Okay, that's A. What's B? I don't know where I am. What's B? B says when radius is. Well, that's not fun. So really, I have no use for the regular area. The thing that's going to help me solve is when we have regular area. And we said it was 105. To solve for the original, like the radius when the area is 105. This is what I need to put into here. Because nowhere in here does it have, because if I put this in for A, which I guess I could have done, and then solved for R, then that leaves the rate gone out of this, and you have to go back and substitute in. It's way easier just to take it into your grade 6 formula or whatever this is and solve for your radius of 10 to get an area of 105. So now that we know our radius, it's just substituting it in again. We know that the dr over dt is still 12. So the rate of the area changing is going to be 2 pi 10 by 12. Feel like we should still leave it in terms of time. 20 times 12, ooh, 240. 2,400. 240. 240. 5 centimeters squared. The last one requires ratios. Are you bringing me a sweatshirt? I did not know what was in here, so I just scratched myself. So I got these pictures up here. This is nice. I forgot one. I forgot what I was playing here. I'm supposed to do that one. Sorry. Yeah, how can you do? Oh, yeah. No, I'll keep it. I didn't even look, and then when you say Kevin, I just love it. I look like a couple hours, and then yeah, I'm gonna like it. He got the hours from his It's big. Oh. All right, last one. Last one, we're trying to pull out that radius again. And you have to do it as a ratio. Grade 9. You learned how to do this? So we want to know what the side length is after 5 seconds has elapsed. Right? That's what the currency is. We're just so excited. So we know that we go 12 centimeters every 1 second. Right? That's what our rate was. So we know that we've traveled, or 5 seconds has elapsed. What's going on up there? 60. So what's happened to the radius? So our question mark is 60 centimeters. It's a distance measurement. And this is our radius after 5 seconds. Now this is where I said assume that your radius initial starts at 0. I cross multiply. 5 times 12 gives me 60. 1 times a question mark gives me the question mark. Only time you cross multiply is when they're on the other side. Really, you're undoing all right. Okay, so dA over dt is equal to 2 pi r, which is 60, times by the rate, which is 12. Oh, it seems like a lot of numbers. dA over dt is equal to 1440 pi centimeters squared per second. So sometimes it's really nice and it gives you straight up what the radius is. And then other times you have to kind of dig that little piece of information out. None of it is beyond your capabilities, but some of it may be beyond your comfort zone. Okay, let's keep on trucking. Okay. Oh, this is a trick question. A ladder 7 meters long is placed up against the wall. Now, realizing at the bottom of the ladder was on a fairly smooth surface, a man started to climb the ladder, and the smooth bottom of the ladder slipped horizontally away from the wall at a rate of 0.75 meters per second. How fast is the top of the ladder falling vertically downward when the bottom of the ladder is 5 meters away from the wall? Huh. It does. It seems like something we can handle, though. Yeah, it's a great little question on steroids. So it gave me some letters here. X is the horizontal distance. What's Y? Vertical. And our last variable? Time elapsed. Okay, what do we know? We know which rate. Do we know how fast we're falling vertically or moving horizontally? So we know dx over dt is equal to 0.75. What else do we know? We know x is 5. All right, so here's the creating the equation part. So you define your variables. And step 2 is create that equation. So this one is pretty straightforward. As you look at this, this looks like a grade 10 basic question in trigonometry. How far up the tree does the ladder hit the wall or whatever? I don't know. It's a right angle triangle. I'm trying to like lead you down the garden path of what equation you need. What do you think? Out of all of your knowledge, look deep inside your brain. What does this remind you of? If it's a right angle triangle, you have no angle. Dig deep. There you go. Sorry, I apologize. So this would be x squared plus y squared equals 7 squared. Do you know the distance of the ladder? So we're going to differentiate x squared over dt. We're going to have the differential of y squared over dt, and you're going to have the differential of 49 over dt. So our equation is going to be 2x times by dx over dt plus 2y multiplied by dy over dt, which is the exact same thing as saying y prime in respect to t. And this is going to be a big whopping 0. I answered the call. Shouldn't do that. Step 1, don't answer phone calls in my class, including me, teacher. Okay. So we did that. So we know that x is 5. We know d of x and d of t is 0.75. Our whole goal is to find that. What's my problem? I need to find out what y is equal to. We did this before. Stuff it into the original equation. 5 squared plus y squared equals 7 squared. So I got 25 plus y squared equals 49. So y squared equals 24. So y equals the root of 24 plus or minus, but what can I reject? The minus, that would mean our letters in the ground, which just seems a little confusing. So now I know what y is. So y is equal to root 24. So now I can substitute all that junk into my equation. So I have 2 times 5 times 0.75 plus 2 times root 24 times by dy over dt equals 0. Too far. So this is going to be 7.5 equals 2 root 24. Nope, that's a box plus equals 0. So I've got dy over dt is equal to a negative 7.5 divided by 2 root 24, which gives me a whopping dy over dt. And negative 0.77 centimeters per second. How come it's not centimeters squared? It's not an area, it's a distance. Does it make sense that there would be a negative? Because where is it going? Down. It's following area, so it has direction attached to it. Okay. Super exciting. Not terribly hard. Creating the equation, maybe? All right. No big. Okay. All right, this looks like fun. Per century. I like when we measure things in centuries. So these things, and I don't pronounce them correctly, staggerling, I think they grow up. And which ones grow down? So in a cave, you know, like when you look at pictures of a cave and there's these like creepy, like kind of rock jutting things like growing, like dripping down off the cave. It was actually a like rock formation that grew. But they also grow upwards as well. So which ones grow down? Ashotosh, are you looking it up or are you just on your phone? Okay, so we are growing from the ground up. So next time you're watching like the new Tomb Raider or something like that, now you know what the things are called. Okay, so there's your, oh no, is that a geography? Geology? I don't know, teacher. Okay, it's always 8% of its height. The radius is always 8% of its height. Its volume is increasing at a rate of 156 pi, that's supposed to be centimeters cubed, centimeters squared, per century. What's the rate of change of the radius when the stegomite is 60 centimeters high? Fun. So what are my three variables? I'll give you my first one. Time elapsed. What are the other things? That's not the thing. What's the information I'm looking for? I'm looking for rate of change of what? The radius. So radius is going to be 1. I'm going to need the height to calculate the radius, but that's something else. And what's the other rate of change that we were given? The height thing, also confused with volume. Okay, so yes, the height plays a key important part of this, but it really doesn't have too much to do with what we're trying to calculate. We know the derivative of the volume in respect to t is equal to 156 pi. We're trying to find what rate the radius increases. Okay? Okay. So this is where the radius height comes together. What relationship is between the radius and height? We know that the radius is 8% of the height. So we know that r is equal to 0.08 of the height. Did you guys hear me? Yes. Maybe possible. Perfect. Well, I guess we do need the height of this. Okay, I was poo-pooing your height needs, but you're definitely correct. Lindsay, do need to do this. Okay, so now we're going to create an equation that has to do with volume, radius, and height. We could do it. Volume, so we're relating volume, radius, and height. Do you guys know this one right off the top of your head? Volume of the cone? Yeah, it's pretty much it. If you can't read it, its volume is equal to 1/3 pi r squared h. I kind of want to do it the other way, just to see if it's the exact same. I feel like I'm maybe not leading you down a parallel path. That's good. So we got to replace a variable, either an h or an r. Which one do you want to replace? You want to replace h? So if we were to rearrange this equation, h is equal to r divided by 0.08. It's a fraction, dude. I don't want to do the fraction. Because why would that be a problem? You're going to have to differentiate that, right? Leave it as a multiplication. I don't know. I think we can do it, guys. I think we can do it. I think we can do it. So volume is equal to 1/3 pi r squared times r over 0.08. Right? So let's tighten this up a little bit. What's 3 times 5.08? 0.08 times by 3. 0.24? Okay. Whew. Exciting. feel the excitement in the crowd. So we're going to differentiate this side. We're going to differentiate. Let's do this. Do we know this?
Yes.
Yes, we know this. Okay, so we know this is 156 pi. If we were to differentiate this, this would be 3 times pi over 0.24 r squared times by dr over dt. I think I did that all right. Ish. I'm looking at what they are doing completely different. So we are trying to find this. Do we know the radius? What is it? So we do know the radius because it told us we had a height of 60. And what do we have to do to that height? Times it by 0.08. Anybody know what that is? 4.8. Hang on. That's the radius. 4.48 or 8? Okay. I'm good. I'm good now. All right. So this one was pretty easy. Seems like a lot of things like that's a bit more fine art. Oh, okay, I don't quite find it. You want me to divide by 5?
It would make it easier.
Well, equals 288 times by dr dt. Now what do I do? Divide. Brilliant. 0.54. What's my rate? What's my unit to measure on my rate? What is that? Okay, just in centimeters. Centimeters per second. Oh, per century. Sorry, yeah. I guess that would be a pretty fast growing thing. Every second, it's like growing half a centimeter. Down there for a little while, you can actually watch it growing. I think we're going to get the last one here. That one's on ratios. It's actually probably the one you're going to need the most, but it's the easiest. I think we can throw it in on Monday.